All right. So also a big welcome to everyone on YouTube and Zoom. Our first speaker is Dan Faulkner, our head of department. He has been in earth science for quite some time. He did his undergrad in Leeds. Afterwards, he did his PhD in Manchester. And in 2003, he finally came to Liverpool after 2 postdocs. And since 2018, he has been head of our department. And today he will tell you something about his talk is 2 words: an understanding of the earthquake process for natural and induced seismicity. So welcome.
Wow, it's fantastic to be starting a new academic year, see so many people. I think this is probably one of the most full this lecture theatre has been for a little while at least, and it is really nice to be here. Although I have to say that I give talks all over the place as well, but always the most nerve-wracking ones are the ones that you have to give to your own department. All right. So I want to talk today just about some whole bunch of kind of like recent work we've been doing. A lot of my research is focused on trying to understand earthquakes, and we've been trying to understand earthquakes for a couple of 100 years. The Japanese started off with big catfish underneath the sea, which is what they thought was responsible for Japanese earthquakes. Things got slightly more sophisticated maybe after the 1906 earthquake in San Francisco, where Reed produced this idea of an elastic rebound, which you stress a fault up and it will suddenly slip and produce earthquakes. And since then we've struggled, I think, to make a lot of headway into really understanding what it is that produces the vast array of tiny little earthquakes that we get every day, and then sometimes these great big whopper events which cause a huge amount of devastation. So I'll be presenting work that's not really been done exclusively by myself, or very little of it has been done by myself, but by a whole bunch of different people here. Mike Allen, who's in the audience, there he is, and a bunch of other people that were involved in a large NERC grant that we had over the past few years, plus some modelling done by a couple of colleagues that in Caltech in the last couple of years as well. Okay. So there's a couple of really good reasons, which I'm sure I'm pointing out the obvious to you all here for studying earthquakes. So first of all, there's a green transition, which we're all acutely aware of that we need to engage with, I think, in the future. And the geological contribution towards that green transition will be to hopefully to start to utilize more things like geothermal energy and maybe store carbon dioxide in subsurface reservoirs. So, whenever we inject any fluids into the subsurface, we produce seismicity, induced seismicity. And trying to get a handle of that, particularly in the UK, as we saw when we tried to start shale gas off a few years ago, is really key, because we're a densely populated little island, and any events that we produce don't tend to go unnoticed at all. So, trying to get to grips with that is hugely important. Natural earthquakes as well. We know that they cause a huge amount of damage to people in terms of loss of life, etc., and also financially in terms of a large cost for each major event that occurs around the Earth. Okay. So the first part of the talk, I'm going to concentrate on induced seismicity. So these man-made kind of earthquakes that are produced from injecting fluids into the subsurface. And this is what Mike did for his postdoc a couple of years ago. And it's really trying to get to grips with some of the issues that we have regarding induced seismicity. So as I said before, this is really important for a number of different industries. And this study really focused on trying to understand the rates of seismicity, so how many earthquakes that we produce when we do inject fluids into the subsurface, but also how big those earthquakes are, because that's what really matters in some ways. People only feel the big earthquakes. And, you know, a couple of examples just here. There was this magnitude 3.4 earthquake under the city of Basel, which might not sound like a huge earthquake, but they drilled this 4.5 kilometer deep borehole directly under the city, and it triggered an event on a fault underneath this large city, and everyone felt it. And that was basically the end of this geothermal project underneath the city of Basel. There's a magnitude 5.4, so much bigger in Pohang in Korea just a few years ago, 5 years ago now. And the Scientific Advisory Board that looked at that event there were in no doubt at all that this event was caused by fluid injection as part of a geothermal project that was started in South Korea. So the plot on the right there just shows the rates of seismicity. So cumulative number of earthquakes against years just here, and you can see things trundling along, and you know, along a relatively linear path here for earthquakes in the central United States. And then around the year 2000, which is when shale gas really kicked off into the US and wastewater was injected into the subsurface, we see a deviation from this long-term trend and a huge increase in induced events that were produced from injecting fluid into the subsurface. Okay, so how do we get an idea on the rate of seismicity, the number of earthquakes, and also how big they are as well? So one way to try to get to grips with this is to look at something called the B value, which is related to earthquake size distribution. So basically, if you plot the cumulative number of earthquakes that you have against how big they are, the magnitude just here, then you get this this linear portion just here, which tells you that for bigger earthquakes, so the bigger events that you get, so 7 is the largest in this data set just here, there are many fewer earthquakes of size. So there's lots of small earthquakes, but there's not many big earthquakes. Okay, and that's described by this equation, which is known, I'm sure a lot of you have heard of this, the Gutenberg-Richter relationship. And it was also probably discovered before Gutenberg and Richter by some Japanese seismologists, Ishimoto and Ida. And basically the B value is the gradient of this plot just here. And the B value, so how steep that is, tells you how many small earthquakes you've got relative to big earthquakes. And if all works well, if we have this linear relationship, then potentially we can use, if we're only recording small events over a short period of time, we might just get a portion of this this data set recorded in any one time. But if we're lucky enough, if we record enough of those small events, we can extrapolate them and try to make some predictions then about how frequently we would expect larger events to occur. And those eagle-eyed people among you will notice that this kind of like saturates and goes flat at these very small magnitudes. And that isn't real, in fact. It's just a product of the instruments that we use to record this data set just here as well. And we have every indication actually that this B value would continue up here to much smaller magnitude of events if we were able to record them. So that's the general message, is that maybe we can use lots of little events if we measure how big they are and how many there are, and we can extrapolate that using this B value to tell us how frequently we might expect to see bigger earthquakes in any particular area. There is quite a bit of argument about whether B values work for predicting the size and magnitude of events, in particular whether things can, these B values can predict the largest magnitude events. And I'm just going to leave that there. If you're interested, there's many papers written on this as well, but this one by Bachman et al. Tells us, well, at least in their opinion, that they think you can use these earthquake size distributions to predict larger events. Okay, so potentially this B value is really important. So so what controls it? What are the underlying things that dictate it? So there's a surprisingly little amount of information on what controls B-values. So there was some experiments done in the 60s by Chris Schultz and again by Mogi in Japan. And their focus was really just showing that B-values were related to how much stress that we've got on a fault or on a rock. So these are some of Schultz's original data. And what he did was he looked at an intact cylinder of, in this case, well, a whole bunch of different rock types just here, so from gabbros to quartzites. And he stressed this rock uniaxially and measured small, really tiny earthquakes that were occurring within these cylinders of rocks, what are called acoustic emissions. And what he noticed is that the more stress you put on these intact rocks, as you go towards the point where you completely fracture them and break them, you create a shear fracture, the B value changed. So the relative amount of small events to large events changed. So that's illustrated by the graph on the right just here. So as a percentage of the failure stress on these intact rocks, so as we go towards the right, we're getting more and more stress on our rock, we're taking it towards failure. Then we actually get a decrease in the B value here. So you'll notice that the B value just here gets smaller as you go up. So as you go closer to failure, you actually get a reduction in your B value as you go close towards the failure. So what does this tell us? So small values of the B value, so say 0.5 as opposed to 1.5, tells you that we've got more large events relative to all the small events. Okay, and if we have bigger values of the B value, this tells us we've got more small events and not very many big events. So what Schultz was saying, I guess, in his work is you take a rock towards failure, then you start to get more and more big events at the expense of all the small events that are happening in there, which kind of makes sense. And honestly, since the late 60s, that's been the prevailing view on what controls B values. People just think it's an indicator of the amount of stress that you've got on a fault. And interestingly, these experiments weren't even done on a fault in the lab. They're done on intact pieces of rock. So, we need to get a better understanding, I think, of what controls B value, if it is this important parameter which might help us predict big events when we inject fluids into the subsurface. So a slightly more recent study, this actually is a frictional sliding experiment. So we've got some model faults now, some synthetic faults in the lab, and they kind of show the same pattern just here as well. So the plot on the right just here shows a whole bunch of measurements, acoustic emission measurements, these tiny little lab earthquakes, again, measured at, in this frictional apparatus at very low values of normal stress. So the normal stress is the stress that pushes the fault together. Okay, and you can see we've got a very steep line just there. Okay, and this corresponds to, well, if you look at the value, the B values that corresponds to, they're quite high values of B value. So lots of small events, not very many big ones. And as we start to push our model fault zone a little bit firmer together, so we go to higher normal stresses, then you need more shear stress to make your fault slide. And the highest normal stress that was used in this experimental setup are these red circles just here, and these correspond to B values which are much lower. So it's the same kind of picture. Okay, that at low stresses the B value is high, so lots of small events, not very many big ones. And then as we go to higher stresses on our fault, we get lower B values, so more big events, less small events. So that seems to support at least Schultz's idea, I think, about B values. So here's something else that can affect B values. So this is some work done by Thomas Goebel, who looked at the effect of fracture roughness on B values. So he did 3 different types of experiments. he produced a cylinder of rock, which we often use in rock mechanics experiments, but with a 30-degree saw cut cut through the cylinder. And he polished that saw cut, so it's very smooth. And then if you put that into a typical triaxial deformation apparatus, like the ones we have down in the lab, you can confine it around the outside by putting it in a high pressure environment. And then if we load it axially, then you get slip along this this very smooth saw cut. So again, he did a similar experiment, but this time he roughened the surface of his experimental fault zone. So the middle one just here, the roughened one. And then finally, they took an intact sample, fractured it naturally in the, well, not naturally, but inside the rig to produce a kind of a very rough fracture, which wasn't a saw cut in this case. So if you have a look at the event statistics that these three different types of model fault zone produce, the fractured, the roughest sample has the highest B value. So in this case, about 1.2. So this tells you that for this very rough surface, we've got lots of little events relative to the bigger events. And for the very polished surface just here, this has got the lowest B value. So this is producing more big events relative to the small ones, which kind of makes sense. Okay, so I want to take you to British Columbia now in Canada. So the group that we worked with as part of this large NERC grant studied a really nice data set from shale gas play in British Columbia. And regardless of what your views are on hydrocarbon production, all the rest of it, you know, this is an opportunity, I think, to have a field scale data set. And you know, I'm always really keen, I think, for somebody who studies tiny little rock samples in the lab to try to think of ways that we can test whether or not the measurements that we make in the lab are really relevant to the bigger scale. So this project was an opportunity to do that. So in this area, they're fracking three different reservoir horizons, which are about 2 kilometers depth in the subsurface. So there are these three horizons down here, the Evie Shale at the bottom, the Otter Park formation just above it, and then the Muskwa Shale just above that. So sitting above these three reservoir horizons, there's a thick sequence of shales. And sitting below here is a dolomitic horizon, actually, in the basement, the Keg River formation. So I think this is, oh, there we go, there's the Horn River Basin, in case you're wondering. And here's a blow-up of the stratigraphy that we've got just here. Okay, so here are our three reservoir horizons. So borehole drilling was taking place just here. They deviated the holes so that they went parallel and right the way through these three reservoir horizons. And then they would basically section off a portion of that horizontal well, increase the fluid pressure to frac, and then move along that horizontal well to produce more gas, I think, along the horizontal bore. Okay, and this is what the seismicity looks like. So overall, there were 10 wells drilled, and in terms of those stages where they section off part of the borehole to inject fluid to frac it, there were 237 stages of fluid injection that took place just here. So the diagram just here shows the three reservoir horizons: the Muskwa Shale, the Otter Park formation, and the Evie Shale. And there's this thick black line just shows where the horizontal wells are drilled through those reservoir horizons. And the dots just here show us where all of the microseismicity occurred related to that fluid injection. So there's a huge amount. There's 150,000 events that were recorded on a very sensitive seismic network, which was installed down some boreholes in this area. And also very small events, so from magnitude -2.4 up to about magnitude 1.5. Okay, so we're talking about really tiny earthquake events here, which might have a source dimension, which is at best maybe a couple of meters across these 1.5 events. Okay, so what you might notice just here as well is that the seismicity that's been produced isn't limited to where the fluid injection took place around these three boreholes. But the biggest events, the ones with the highest magnitude shown in these kind of orangey colors, actually occurs in the underburden, in this dolomitic underburden, which sits below the three reservoir horizons. And in fact, these large events are picking out fault structures, which are being reactivated because of the fluid injection. Okay. So I think one of the criticisms in the past for using B values to try to predict seismicity is that when you do fluid injection experiments, you produce lots of tiny little events, which may be within the rock mass, but not focused on a fault in the subsurface. But if we're interested in the big events, the big earthquakes that can form, they're only going to happen on pre-existing faults that we've got in the subsurface. You're never going to be able to create, a several kilometer long fault just by fluid injection to produce an event which is maybe, maybe I don't know, magnitude 4 or 5 in that case as well. So we're only going to produce large events on pre-existing fault structures. So the first thing that we did, looking at this microseismic data set, was to try to separate out these small events, which were just happening in the reservoir horizons, from the seismicity that's occurring on pre-existing fault planes. So we did something that's called clustered seismicity. It's not done very often, but what happened is that we looked for planar structures within the reservoir just here, that are being illuminated by the microseismicity and that are pre-existing faults. Once we'd identified those, our cluster analysis just picked the events which were in close proximity to these fault planes, and we separated those out from this cloud of grey events just here, which are not associated with any discernible pre-existing fault structures or planar structures within the rock mass just here. Okay, so here's just an animated GIF just showing these planar structures just here. You can see them at some angles better than others, and the coloured ones are the ones that we used in our analysis to look at faults just here, and the grey ones are just the ones that we're not interested in, because their statistics and their size isn't going to tell us anything about a large magnitude seismic event that could happen within the reservoir. They're only going to occur on the faults. So it's the coloured dots that we're interested in looking at. Okay. And here are some of the B values. So again, just like that early plot I showed you, we've got the number of events along the y-axis just here, and the size of them, the magnitude along the x-axis. And the clustered events that we looked at, the ones associated with faulting, are these clustered events are the low B value ones, so they are the red and the orange events just here. Okay, so they're associated with B values around 1, which tells us that we've got quite a few large events relative to small events, which you'd expect for faults. And all of the other ones, the clouds of seismicity in there, have very high B values, which tells you you've got lots of small events, but not very many big events, which is what you'd expect if you don't have any pre-existing faults. Okay, so what was new and novel, I think, about this study was that we are able to try to relate the seismicity that we see just here. We can further subdivide our clustered events into stratigraphic horizons, so that we can look at what the B value is around faults which exist solely within the Muskwa formation. And we can see whether that has any difference in the B value for events on faults that occur within the Otter Park Formation, etc. So the idea is that we would take material collected from boreholes from each of these different horizons, and we would measure their lab properties. And that's what I want to move on to a little bit just here as well. So we kind of ran shearing experiments as well. So we took the crushed material that we've collected from borehole and we shear it under high pressure, basically simulating the conditions at 2 kilometers depth in British Columbia in one of our triaxial apparatus. So we use this kind of like this direct shear assembly, which we developed in Liverpool a few years ago. And I'll show you some of the data that come out from this. So the bottom left just here shows some experimental results. And we've got slip displacement just here. So we take our layer of crushed material, we load it up. So this portion of the curve just here is it's being loaded up elastically. And then at some point it will yield and start to slide. Okay, and the stress level at which it slides tells us something about the strength of these materials. So that's this parameter mu, the friction coefficient, which, just to remind you, is the ratio of the shear stress that you have to apply relative to the normal stress that you've got on a fault plane. You'll also notice that there are these kind of like perturbations on each of these friction curves just here. Well, first of all, we can see that there's quite a range of strengths that we get in these different materials. So the blue ones, the lowest strengths here, are from the clay-rich overburden shales. Okay, and the strongest material that we have is this purple material, which is from the Keg River Formation, the underburden, which some of you will remember is where we got all of the big events with the recorded in the seismicity. Okay, so these little kind of perturbations on the friction curve here are produced by changing the slip velocity, or the displacement rate at which we're sliding our little model fault zone. So this illustrates the principle just here. So we go from maybe slow sliding to slightly fast sliding. It's a bit of a stretch to call it fast, because we're typically going from about 0.3 microns per second up to about a mighty 3 microns per second. So fast is stretching things a little bit. But the reason we do this is to try to get an idea of how the strength changes as we start to slide our fault a little bit faster. And this gives us really important information about how earthquakes nucleate, okay, and leads to two different types of behavior, particularly. So what's illustrated just here is something that's called velocity weakening behavior, okay, where here's the frictional strength of our rock to start with at this slow sliding velocity, okay, and as we change to a slightly faster sliding velocity, the first thing we see is a jump in the strength, and then it evolves over some kind of characteristic slip weakening distance to a new steady state strength down here. So this immediate effect is characterized by something called A, and the kind of evolution effect just here is characterized by something called B. And I apologize right now because I'm bringing together seismology and lab studies, and there's B's in both of those, so it gets very confusing as to which B I'm talking about. Okay, but for the lab stuff, I'm only ever going to talk about the combination of these two parameters, so A minus B. And where A minus B is negative, which means that the drop here is bigger than the rise that we've got just there, this tells us that our little model fault zone actually becomes slightly weaker when we start to slide it faster. All right, and that's really important because that's the only way that we can produce instabilities. So if you start to slide your fault a little bit faster, it becomes weaker, so it starts to slide a bit faster again, and then there's a kind of like a feedback loop there which can produce an instability. So negative A minus B's are what we call velocity weakening behavior or rate weakening behavior, and this can potentially nucleate earthquakes. On the other hand, if we've got velocity strengthening material, as we start to slide our fault a little bit faster, B would be less than A, so that the new steady state sliding strength it is actually slightly greater than it was before. Okay, and if that's the case, then we can never nucleate in the instabilities. We're going to stabilize the fault slip, and what would result is fault creep, like we see on the central part of the San Andreas Fault, where the fault just moves at the plate rate at about 35 millimeters every single year. So, these friction values here, we often think of faults as producing earthquakes when we just take them to failure. That's not always the case. We can take a fault to failure by increasing the fluid pressure or increasing the stress on that fault. But in actual fact, what occurs when you take that fault to failure very much depends on the frictional parameters just here. So sometimes we can just produce steady fault creep. Sometimes we can produce earthquakes, and that's dependent on the material properties that we've got. Okay. So our goal here was to try to relate the seismic values that we've got here, these B values, to this lab measured frictional parameter A minus B, which tells you whether things are velocity strengthening or velocity weakening. And the central panel just here, outlined by the red box, just shows the variation in B values, which are shown by the joined line, the small white triangles, sorry, diamonds, joined by a black line just here. These are the seismic B values, okay? And there's variation as you go through these different reservoir horizons into the underburden just here, and this is the overburden just there. And I should point out that these B values in the central panel are the ones that are determined from our cluster analysis. So they're the ones that are happening on pre-existing faults. And it's fair to say we were pretty chuffed with this, Mike, weren't we? Because visually at least, the correlation between the lab measured A minus B values, which are shown by the colored dots just here, they kind of track the variations in the seismic B values quite nicely. So, for many years since the late 60s, people have always tried to relate variations in the B value to the level of stress, whereas we've actually shown that there's a strong possibility that these B values are controlled by frictional parameters that we have on the fault zone. So if you just look at all of the events, so the ones that are not on fault planes as well, there's a really poor correlation between our measured lab values and the B values and the seismic B values that you see. And if you strip away just the faulting events and look at those, look at the unclustered events, again, there's a really poor correlation. So a pattern only starts to emerge when we have a look at our lab data, which are measured on simulated faults, with the actual events that are occurring on faults in the subsurface. Okay, so this isn't the end for those of you that are just thinking, yeah, that was quick. But just to wrap up this little bit of the talk, the reason why this is important, I guess, is that we've shown that there's a material parameter relation, which seems to correlate well with the magnitude and rates of seismicity that we see. So what this means is that if we tie this down and understand this a little better, there's a possibility that we could drill a hole into the subsurface where we're thinking of injecting for geothermal or CCS or anything really. We could measure the frictional A minus B values, and we could make a prediction about the rates and size of seismic events that we would produce if we did inject fluid into the subsurface before we do any kind of fluid injection there as well. So it's a way to try to pre-predict what might happen. Okay. So I just want to follow on from this study by thinking on the bigger scale as well. So I'm fascinated by big earthquakes. Okay, I mean, those are the ones that always make the news headlines, right? You never hear about magnitude 1.5 events on the BBC very often, right? And these are the freaks, to be honest, as well. We have this Gutenberg-Richter relationship with a b-value of 1, which I should have said, actually, a b-value of 1 tells you that you have 10 times as many magnitude 6 earthquakes as magnitude 7 earthquakes, and 10 times as many magnitude 7 earthquakes to magnitude 8 earthquakes. So as we go up the scale of magnitudes, the really big earthquakes, the magnitude 8s and even the magnitude 9.5, they don't happen very often, maybe once every few years globally. It's a difficult thing to study these freaks of nature, the ones that for some reason just happen really, really rarely, but those are the ones that we want to try to understand, right? Because they're the ones that do all the damage. Okay, so let's just start by having a look at the San Andreas Fault. So this is the central portion of the San Andreas Fault. So north is shifted around a little bit just here. And it's the creeping section. It's the bit that is moving at about 35 millimeters every single year. At the southern end, just here, there's a repeating magnitude 6 earthquake, which happens on average about every 22 years. So this was a study by the group in ETH in Zurich, who looked at seismicity that was occurring on this creeping section. And what we're looking at in these panels just here, so I shouldn't point for the people on Zoom. What we're looking at in these panels just here is we're looking at the actual fault plane itself. So we're looking at a prediction of the fault plane. So we've got depth down the left-hand side just here, and then this is along the strike of the fault. And the colors that we can see are events that occur on that fault, which have been analyzed in terms of their B value. So in Schulem and Wiemer's paper, they interpreted this to be showing us what stress levels were on the fault zone. And I think from our study, what I presented from the Horn River Basin, I look at this plot now and think this is perhaps telling us what the variation in material properties are along that fault. And interestingly, this little region just here with the kind of like the blue and the red colors, this is where B values are very low. So this is where you get more big events and less small events. This region here is where the magnitude 6 earthquake happened. The last one was in 2004. So these stars just here are showing the hypercenters of previous earthquakes just there. And if you believe our study, then these low B values are related to velocity weakening materials. So this is exactly where we would expect earthquakes to happen. And in areas where the B values are very high, so in these regions just here and maybe these green regions, that would be related to velocity strengthening materials, and this is where we would expect fault creep, and that's exactly what you see in California. Okay, so just moving on to how we think about these big ones here. The data from the Horn River Basin that I showed you are tiny events. Okay, and the kind of analysis that we're doing on those by looking at these very slow slip velocities in the lab and trying to figure out whether things are velocity strengthening and velocity weakening. That might apply to these really small events, but when you have monsters, when you have really big seismic events, then there are a whole host of other processes which start to kick in, which might start to wipe out that relationship between lab measured A minus B and B values, seismic B values. So we have to kind of have a different approach to studying these big events, I think. And the scale at which we do our lab experiments isn't really enough to capture what's going on just there as well. So so we've been working for a number of years now with a modeling group in Caltech who produce these beautiful models which basically take our lab data as best they can, and they try to predict sequences of earthquakes, so numbers of earthquakes that happen on a fault which they can just load up in their numerical models. Okay. So there's a couple of things just to say about modeling to start with. I'm not a modeler, so a lot of these things are tricky for me to understand, but A famous mathematician last century said with about modeling, said with 4 free parameters, I can fit an elephant, and with 5 free parameters, I can make it wiggle its trunk. And what he's saying is that if you put too much into a model and make it overcomplicated, you can predict whatever behavior that you want, okay? And then the insights you get from that model are pretty limited. At the same time, we've got to make sure that the right ingredients are in the model to capture all the physics that are going on too. So that kind of leads on to this second quote by Einstein, which says that everything should be made as simple as possible, but not simpler. And then finally, it's worthwhile just pointing out that all models are wrong, but some are useful. So in terms of the Caltech group's models, the thing I like about them is they have a minimal amount of physics, but what is in there really represents, I think, the key parameters that occur during earthquakes. So it's a very complicated slide, this. Bother from, but really what I want to point out just here is that we start on the left-hand side just here. We start with rate and state friction, which we kind of reviewed a few slides ago. So we have lab data which informs some of the physics that happens just here. The model basically just embeds a fault into an elastic medium. We have something called thermal pressurization, which I'll talk about in the next slide. And then from this, as we load this numerical fault now, we produce sequences of earthquakes. And because it produces sequences of earthquakes over sometimes many hundreds of years, that gives us an opportunity to study the number of small events and the number of big events, which gives us p-value statistics to be able to compare with what we see in nature. Okay. So here's rate and state friction again. This is just what goes into the model. I won't dwell very long on this slide. So velocity weakening and velocity strengthening type of behavior that we talked about before. And an extra thing that is built into these models, because they're big earthquakes, the slip velocity on the faults reaches quite high levels. And something we've learned, I think, in the last 20 years or so is that as we increase the slip rate, okay, so these are kind of seismic slip rates at about 1 meter per second. So down here, these are really slow kind of earthquake nucleation velocities. So at 10 to the -6, this is a micron per second. This blue window here just shows where plate motion kind of sits in this picture. So we have to go from plate motion rates up to earthquake rates if we want to produce an earthquake. But if we do produce a big earthquake and get up to slip rates which are 1 meter per second, then something we notice is that the friction coefficient, the strength of our fault, drops off dramatically. So things get much weaker when we slip things faster. And there's a number of reasons for that, a huge number of co-seismic weakening mechanisms, as we call them. But the one in the model is thermal pressurization. So we all know if we've got cold hands, right, we press them together, so put a bit of normal stress in, and if we rub them fast enough together, so we've got high slip velocity, your hands warm up. Yeah, and exactly the same things happen in faults. And if there's fluids contained within fault zones just here, they become pressurized by this temperature increase. And the temperature increase is pretty significant, actually, at the kind of depths that big earthquakes happen at. So there's a couple of equations here. One just shows the temperature evolution with time as we heat things up. And the second equation here just shows you or tells you how the pressure evolves with time as well. As we increase the fluid pressure in our fault, this kind of pushes the plates apart a bit, if you want, and reduces the amount of shear stress that we need to be able to slip our fault. Okay. All right, so I think, until a few years ago, I used to think of faults in a particular way. It's elastic rebound theory, where you stress a fault up to the point where it's at its failure stress, and then it will just slip. Well, these models kind of illustrated to me, at least, that that isn't always the case. Because if we just have a look at the right-hand side panels just here, this one to start with, The kind of orangey dashed line just here is the failure stress, or the stress that you need to slip your fault. And the grey line that we've got here, I think it's grey, not quite sure, is it green? Slightly colourblind, there's two in there. But anyway, okay. The green line here just shows the shear stress that we've got on our fault. And you'll notice that in this region, just here, so we've got a picture here actually of our, onto our fault plane. So we're looking at stress levels on our fault. Okay, so the stresses here at the edges are quite high, and in the central part just here, they're very low. So the stress on the fault here is nowhere near enough to be able to get the fault to slip. So what's interesting is that these regions where the stresses are high, as we load our numerical simulation just here, this produces small events. Okay, as those small events start to propagate, they propagate into this region of very, very low stress on the fault. And as a result, they don't make it very far, they just die out. There's just not enough stress on the fault. But in this case, this tiny little event that you can see just here, so this is a slip along this axis. What it does do is it leaves a little spike of stress where it dies out. So it kind of introduces a little stress concentration into onto the fault plane. So the next event that occurs, this little one just here, nucleates from the opposite side of the model and propagates towards the right. But this dies out too because it hits this low stress region, but it leaves this spike of stress in here. And this happens again and again until we reach this situation just here, where a number of the small events here have changed the stress distribution on our fault. So there are small places just here where the stresses are actually high enough to create slip on our fault. But in between them, the stress levels, the shear stress on the fault is still way below what we would need in order to start faulting in this region, for example. But it just so happens that the next event that occurs on this fault is big enough that it can run through this low stress region just here. In fact, sorry, it starts over here. So it's big enough that it can run through this low stress region. Okay, and as it gets bigger, there is more of that dynamic weakening, that thermal pressurization that we get, which actually increases the stress concentration at the rupture tip, and it allows it to plow through ever lower values of shear stress that pre-exist on the fault. So this big event that happens here is basically able to propagate right the way across this model. It's a model spanning event. So this is the pre-stress shown in grey, and then the final stress after the earthquake's happened is this very, very low shear stress level at the base just here. So models like this kind of changed my view. I was taught that all faults are critically stressed. They're at the point of failure, and all you have to do is drop an extra straw on the camel's back and you'll get an earthquake. These models tell us that as long as the stress somewhere on the fault is high enough to nucleate an earthquake, that earthquake may be able to propagate through some pretty understressed parts of the fault, which really don't have half enough stress on them in order to slide the fault. But because it's a dynamic event and at the rupture tip, we get this big stress concentration that can plow through these low stress regions. Okay, so we're just going to have a look at the video of that last event that happens now as well, which nucleates on the right-hand side and then propagates right the way across. And we can see the growth of this earthquake event, this big event, this model spanning event in terms of slip on the top panel. Okay. How am I doing for time? Okay, not that. All right. Okay, so what this plot here just shows from a number of models that we ran is it basically shows along the x-axis, this is illustrating the average level of stress, shear stress that we've got on our fault before an earthquake event happens. Okay, each of these dots plotted just here is an event in this sequence of earthquake models. Okay, and along the bottom axis here, we've got huge events on the right-hand side and small events on the left-hand side. So what this tells us is if we just have a look at the red data to start with, okay, it tells us that the bigger earthquakes that we have just here, they're able to plow their way through ever lower values of pre-stress on our fault zone. Okay, and also the more efficient dynamic weakening that we have, which might be produced by lower permeability fault rocks, for example, which produces more efficient thermal pressurization. The more efficient weakening that we have, the more this pattern is accentuated. Okay, so the more the fault weakens when we have an earthquake, the more it is able, the bigger the earthquake gets, to plow through these low stress zones. Okay, so why is this important? Well, it kind of feeds into the B values. So the two plots that we've got on the right-hand side just here, these just show the occurrence of events of different sizes in these earthquake models. And then on the right-hand side are the plots that we're more familiar with, the cumulative number of these earthquakes against their size. And at the top just here, we've got not very efficient dynamic weakening, whereas at the bottom, we've got very efficient dynamic weakening. So the dynamic weakening is essentially the equivalent of that A minus B parameter that we measure in our slow slip experiments in the lab, but it's just scaled up for high velocity slip. Okay, so when we have very efficient dynamic weakening, this produces lots of big events, these model spanning events, and not very many small events at all. Okay, and if we don't have very efficient weakening during our earthquakes, then we end up with higher B values and we end up with more small events and not very many large events. And I just want to briefly say why this might be. You know, one interesting thing which has puzzled seismologists for a while, I think, is that this is the southern part of the San Andreas Fault. So we've got LA somewhere around, where would it be? Somewhere around here, I think, going up towards Parkfield, the central part of the San Andreas Fault we've got just here. So this is southern California, the southern part of the San Andreas Fault. This part here last ruptured in 1857, the Fort Tejon earthquake. It was a bigger earthquake than the 1906 earthquake that happened around San Francisco. But what's been puzzling people, I guess, are these areas where very, very few earthquakes, even small ones, have been recorded on the southern San Andreas Fault. Okay. So there's a number of ways to interpret that. Maybe, you know, the fault is strengthened and we're not producing many earthquakes on there. You know, from the modeling that we've done, I think one suggestion for why we've got these really quiet, seismically quiet parts of the fault here is that when we do get an earthquake happening on the southern San Andreas like that, it's so huge, it basically just reduces the shear stress that we have after the earthquake on the fault to almost zero. Now, if that's the case, it would take thousands of years to build up the stress on these sections just here to levels where we could critically stress the fault. But the point is that we don't need to critically stress that fault. We just have to have enough pre-stress on there, which might be quite a bit lower than the failure stress. But all we need to do is nucleate an earthquake to the south or to the north. And if the stress conditions are right, it will rupture through this critically understressed part of the fault zone and produce a big earthquake. So this might tell us some of the reasons why it's really difficult to predict these big earthquakes. It's not as simple as understanding what the stress level is on the fault zone. We might drill this fault zone and find the stress levels are really low. We just say, hey, well, you know, we don't have to worry about earthquakes on the southern San Andreas Fault because the stress levels are low. But that's not the point. If we get nucleation of an earthquake somewhere else, if it produces a big enough event, that can propagate through very understressed parts of fault zones, which is part of the reason why I think earthquakes are potentially, well, they are very, very difficult to predict. Okay, so some conclusions from that part of the this part of the talk. So first of all, that B value variation that we showed on the Parkfield section of the fault, I think, the possibility is now is that's reflecting, well, the new view maybe is that that's reflecting material properties rather than just stress levels on that fault. And then finally, just what we talked about is these areas of seismic quiescence, these areas on big faults where there's very few events. That might be telling us that those portions of the San Andreas Fault, when we do get big earthquakes on those, there's very efficient dynamic weakening that takes place, which allows a big event to form, which can plow through these critically understressed parts of our fault zones. And with that, I'll leave it there. Thank you very much.
Thank you. Are there any questions for Dan? Hold on.
Very nice book. So just a bit of off-the-wall question. You said that big earthquakes can only happen through this fault. What about when those faults originally come from? What about fault initiation? Is that all the series of small events, like anything that are pre-existing ones, or is it a regular one?
Yeah, my feeling is that faults have to grow incrementally. There are different scaling relationships to the amount of displacement you need on a fault regarding its length. So displacement length relationships for faulting for faults are different to displacement length scaling relationships for earthquakes. So the ratio is about 1 to 100, I think, for faulting, which means that for a meter of slip, your fault's about, on average, about 100 meters long. Whereas for a meter of slip in a magnitude 7 earthquake, for example, your fault would have to be 10 kilometers long. So there's different levels of stress that's released. So I think the prevailing view is that you couldn't have, bang, a great big fault formed in a huge seismic event. You'd probably incrementally grow your fault because they're more difficult. They've got to plow their way through intact rock around the fault tips. And only then, when you've pre-prepared that fault, then can you have some earthquakes on there that will produce big events.
Let's use Casey.
I'm wondering, the models that you showed are very confusing, and then clearly, given the right conditions of stress, they seem to be propagating regardless of those conditions elsewhere on the fault. So does this suggest that perhaps the concept that you talked about earlier on the material properties of velocity weakening and velocity strengthening need to be rethought in that respect, because they acquire a lesser prominence in the others?
Yeah, it's exactly right. I don't know whether I said that clearly enough, Betty, but you're exactly right. The lab measured properties really tell you about earthquake nucleation, and they may be relevant to small events where the slip velocities don't get up to very high and the slip displacements are not very much, so you won't produce heat to produce dynamic weakening mechanisms. But I think for the bigger events, so for example, the Horn River Basin, we only ever get up to a maximum of magnitude of 1.5 there as well, so they're tiny little events. But if we want to think about natural seismicity, things that get up to magnitude 4, 5, 6, then there's a whole set of different processes which will wipe out basically the effect of A minus B. But dynamic weakening mechanisms, they basically tell you how much the stress drops from during your slip event. So the faster you slide, the more heat you produce, the bigger that stress drop is, you get more efficient dynamic weakening, which is analogous, if you want, to slow slip, where A minus B tells you how much your fault will weaken as you start to slide it faster. So there's probably a continuum of from A minus B to dynamic stress drops that you see in there as well. And we might be able to use A minus B for the very small events, but anything larger, we're going to have to try to think about the dynamic stress drops. And the dynamic stress drop very much depends on a whole bunch of different factors. The elastic wave field, all of these different things, which is why you have to use these models. It's really the only way you can do it. You can't do it in experiments because it's such a coupled system.
That was really interesting. I'm kind of thinking about implications of this one. I'm going to put it in context of how we what geothermal structure is that. And we use critical stress theory for geothermal model construction. We hear that where faults are likely to dilate or slip for fluid flow that can be so obvious that like how to drill into
Yeah.
But thinking about this, do we now need to sort of avoid like this that just because the way we currently model the state of slip or open dilation of the structures, just because it's not showing up with that dilation slip doesn't mean they're not necessarily moving and open and potentially flowing.
Yeah. So the nice thing about this is it doesn't particularly contradict that. We've known for a while that plate boundary faults, so whack and great, big faults, seem to show this weakness. Okay, whereas intraplate faults, the smaller faults that happen in continental areas, seem to be critically stressed. The stress analysis that we do suggests that the shear stress resolved on them is actually quite high, not low like what I showed just here. So going back to this plot, it shows that for small faults that we might have in intracontinental regions, you still have to have pre-stress on your fault to get any earthquake propagating through there, which is quite close to the failure stress. So probably the scale here doesn't mean very much, rupture length over the theoretical nucleation size, but essentially over this side of the plot here, you have to have plate boundary faults. These are huge faults, and they're the only ones that can produce, the magnitude 7, magnitude 8 earthquakes. And most of the ones that we have in intracontinental regions are on this side of the plot just here, and they're just not big enough to be able to produce very large events. And because of that, because they're not producing large events, there's not very much dynamic weakening, and as a consequence, the stresses on those faults has to be quite close to failure. So in actual fact, this analysis is nice because it fits with that picture that small intracontinental faults still have to have high stresses on them, which is the observation that we have, and they're kind of critically stressed. But the really big plate boundary faults have this, are big enough to be able to host really large events where strange things might happen and we get a lot of dynamic weakening, and then they'll be able to plow through potentially areas of really low stress on there as well. In actual fact, we see that. So stress measurements around the San Andreas tell us that the resolved shear stress on the fault is really low, way below what we would expect to produce faulting. And this is one explanation for why that might be.
More questions?
Just to follow up,
Yeah.
So thinking about the whole boundary level structures, is this potentially something to think about when we're trying to explain regions of slow slip on subduction interfaces, for example?
Oh. Yeah. No, slow slip is it's something we're both interested in, right? I was in a meeting in Japan the week before last, which was slow to fast earthquakes, and the actual mechanisms of those is still a bit obscure. It's still very obscure, I think. And I talked before about velocity strengthening, velocity weakening materials. So when you take a fault to the point of failure, it might just creep, or it might produce an earthquake event. There's some middle ground which we don't quite understand at the moment, where things get going, but they don't go to kind of like earthquake slip speeds. There's something that limits those, and quite what that is, which allows some to pass through that barrier and go on to be regular earthquakes with all the properties of those, and what limits them to really kind of their instabilities. They're faster than the loading rate that's on the fault, but they're not going to seismic slip rates for some reason. Those are just a fascinating beasts. They really, really are. And, you know, that's an area where there's lots of active research going on at the moment, and we have a grant to try to understand that.
Thank you. Unless there's any other questions on the Zoom, or I'd say another big thank you to them. And I think that concludes the first seminar of this series. And next week, I hope you're all back here at 3:30 for Peter Allen, who's coming in from Bristol, and talking about volcanologists that all need to be sedimentologists. So that'll be an interesting talk. Those who are interested, I think we are continuing in the pub